Hello, and welcome to the Late Lab. Before settling in, if you enjoy these videos, please take a moment to like the video, and please consider subscribing to the channel if calm journeys through science help you relax or unwind. And while getting comfortable, please feel free to share where this video is being watched or listened to tonight. Whether it is from a quiet bedroom, a late-night train ride, a softly lit living room, or somewhere far across the world, it is always lovely to see where everyone is listening from. Whether from a quiet bedroom, a late train ride, a softly lit living room, or somewhere on the other side of the world entirely, share the location in the comments below. It is a strangely fitting question for tonight's topic, because in the world of quantum physics, the simple idea of where something is turns out to be far less straightforward than it first appears. For most of everyday life, the universe feels solid, predictable, and reassuringly logical. Cup sits on a table. A chair remains in the corner of a room. Light travels from a lamp and illuminates the walls. Objects move from one place to another along clear paths through space. These assumptions feel so natural that they rarely invite much thought. Yet beneath that calm surface lies a layer of reality where the familiar rules begin to bend. In this hidden world, particles can behave like waves. Objects can exist in several possible states at once. Two particles separated by enormous distances can still appear mysteriously linked. And the simple act of observing something can sometimes change the outcome of an experiment. These ideas sound less like traditional physics and more like philosophical puzzles. Yet they are not speculation or imagination. They are the results of careful experiments carried out over more than a century by scientists trying to understand how nature behaves at the smallest scales. The field that emerged from these discoveries is known as quantum physics. At first glance, quantum physics seems almost playful in its strangeness. It introduces ideas like particles passing through two openings at once, electrons appearing in probability clouds rather than fixed orbits, and light behaving both as a wave and as a particle depending on how it's observed. But beneath that strange surface lies something remarkable. Quantum physics is not an obscure theory about distant particles or laboratory curiosities. It quietly governs the behavior of atoms, molecules, and the very structure of matter. Every solid object, every chemical reaction, every star, and every living cell is shaped by quantum laws, operating far below the level of human perception. Even many of the technologies used in everyday life, from smartphones to medical imaging systems to modern computers, rely directly on the strange rules uncovered by quantum physics. And yet, despite more than 100 years of research, many aspects of quantum theory remain deeply puzzling. Physicists have learned how to use quantum mechanics with extraordinary precision. They can predict experimental outcomes to astonishing accuracy. But when it comes to explaining what the theory truly means about the nature of reality, the answers are far less settled. Some interpretations suggest that multiple possible realities may coexist. Others propose that information itself may lie at the foundation of the universe. Still others hint that space and time might emerge from deeper quantum processes that remain only partially understood. These ideas are not fringe speculation. They are topics actively explored by physicists at research institutions around the world, from the Perimeter Institute for Theoretical Physics to CERN, from the University of Vienna to laboratories studying quantum information and quantum gravity. Tonight's journey explores this strange landscape. It begins with a time when scientists believed physics was almost finished, when only a few small puzzles remained. From there, a series of experiments slowly revealed that nature behaves in ways far stranger than anyone had expected. Along the way, discoveries about light, atoms, probability, and information gradually reshaped humanity's understanding of the universe. The deeper scientists looked, the stranger things became. So settle in, relax, and let the mind wander gently through one of the most fascinating ideas ever uncovered by science. Because when it comes to quantum physics, the deeper the investigation goes, the clearer one truth becomes. Reality is much stranger than it first appears. For much of the 19th century, physics appeared to be a finished puzzle. The great laws describing the universe seemed already discovered, written down with elegant mathematics and confirmed again and again through experiment. To many scientists, the fundamental rules governing matter and energy felt settled, almost comfortably complete. At the centre of this confidence stood the work of Isaac Newton. More than 2 centuries earlier, Newton had introduced the laws of motion and universal gravitation, showing that the same principles guiding a falling apple also governed the movement of the moon and the planets. His framework of classical mechanics described how forces influence motion, allowing scientists to calculate trajectories, predict collisions, and understand the mechanics of everything from swinging pendulums to planetary orbits. The success of Newton's mechanics was extraordinary. Engineers used it to design bridges and steam engines. Astronomers used it to predict the return of comets and the positions of planets decades into the future. The motions of the solar system unfolded according to equations that worked with astonishing reliability. Then, in the 19th century, another remarkable achievement arrived. The Scottish physicist James Clerk Maxwell developed a set of equations that unified electricity and magnetism into a single framework known as electromagnetic theory. Maxwell showed that electric fields and magnetic fields are not separate phenomena, but 2 aspects of the same underlying process. More surprisingly, Maxwell's equations predicted the existence of electromagnetic waves travelling through space at a specific speed. When that speed was calculated, it matched the known speed of light. Light itself, it turned out, was an electromagnetic wave. With Newton's mechanics explaining motion, and Maxwell's equations explaining electricity, magnetism, and light, physicists believed they had uncovered the essential rules of nature. There were still details to investigate, of course. Measurements could be refined, and particular systems could be studied in greater depth. But the broad picture seemed complete. One of the most famous expressions of this confidence came from the British physicist William Thomson, later known as Lord Kelvin. In the late 1800s, Kelvin remarked that physics was essentially complete, aside from what he described as 2 small clouds on the horizon. These were minor puzzles that seemed unlikely to disturb the underlying structure of physical law. The comment reflected the mood of the time. The foundations of physics appeared solid and stable. Many scientists believed that future discoveries would simply refine existing theories rather than overturn them. Yet those 2 small clouds would prove far more important than anyone expected. The first cloud involved the nature of light and the mysterious substance believed to carry it through space. At the time, physicists assumed that light waves must travel through some kind of medium. Sound waves move through air, ocean waves move through water, and vibrations travel through solids. It seemed natural to assume that light waves also required a medium. This hypothetical medium was called the luminiferous ether. The ether was imagined as an invisible substance filling all of space. It would be extremely thin, so thin that planets could move through it without noticeable resistance, yet stiff enough to carry waves of electromagnetic energy across enormous cosmic distances. If the ether existed, Earth should be moving through it as the planet orbited the Sun. That motion should produce a detectable effect, somewhat like the way moving through air produces a breeze. Light travelling in the direction of Earth's motion should move slightly differently, compared with light travelling across that motion. Detecting this difference would reveal the presence of the ether. Testing this idea required extremely careful measurement. In the 1880s, two American physicists, Albert Michelson and Edward Morley, designed an experiment capable of detecting tiny differences in the speed of light depending on direction. Their instrument, called an interferometer, split a beam of light into two separate paths arranged at right angles. Each beam travelled along its own path, reflected from mirrors, and then recombined with the other beam. If Earth were moving through the ether, one beam of light should take slightly longer to travel its path than the other. When the beams recombined, the difference would create a subtle shift in the interference pattern. Michelson and Morley performed their experiment with remarkable precision. The apparatus was mounted on a massive stone slab floating in a pool of mercury, allowing it to rotate smoothly and isolate it from vibrations. The level of care involved was extraordinary, but the result was even more surprising. No difference appeared. Light travelled at the same speed in every direction, regardless of how the apparatus was oriented. The experiment had been designed to reveal the motion of Earth through the ether, yet the expected effect simply refused to appear. Repeated measurements produced the same result. For many scientists, this was deeply puzzling. If the ether existed, the experiment should have detected it. If the ether did not exist, then the prevailing theory of light would require reconsideration. At first, physicists attempted to preserve the existing framework by proposing modifications. Some suggested that the ether might be partially dragged along by Earth. Others proposed mathematical adjustments that would cancel out the expected effects. But none of these explanations felt entirely satisfying. Meanwhile, experimental physics was becoming increasingly precise. Institutions such as the Cavendish Laboratory at the University of Cambridge were developing a reputation for careful measurement and innovative experimental techniques. Physicists were constructing instruments capable of detecting incredibly small effects, sometimes measuring quantities smaller than a billionth of everyday scales. With improved precision came improved scrutiny. Subtle discrepancies between theory and observation began appearing in different areas of physics. At first, these discrepancies seemed minor. They were treated as technical puzzles that would eventually be resolved within the existing framework. Yet some of these puzzles stubbornly resisted explanation. One of the most persistent involved something surprisingly ordinary. When objects are heated, they emit light. A piece of metal placed in a furnace gradually begins to glow. At lower temperatures, the glow appears red. As the temperature rises, the colour shifts toward orange and then toward bright white. Physicists began studying this phenomenon carefully, measuring the spectrum of radiation emitted by heated objects with increasing precision. The measurements revealed a pattern that classical physics could not reproduce. The equations describing electromagnetic radiation predicted behaviour that simply did not match what experiments observed. At first, this discrepancy seemed like a minor technical issue, but as measurements improved and calculations became more refined, the gap between theory and observation became impossible to ignore. The familiar laws of physics, which had seemed so complete only a few years earlier, were beginning to show cracks. The universe, it seemed, was keeping secrets, and one of those secrets was hidden in the glow of heated matter, waiting for a physicist named Max Planck to begin unravelling it. As the 19th century drew to a close, physicists found themselves facing a puzzle that seemed strangely out of place among the otherwise confident laws of classical science. The puzzle did not involve distant galaxies or mysterious forces in deep space, It involved something far more familiar. It involved heat and light. When an object becomes hot enough, it begins to glow. A metal rod in a furnace slowly turns dull red, then orange, then bright yellow, and eventually white as the temperature increases. This change in color is not random. It reflects how energy is being emitted at different wavelengths of light. By the late 1800s, physicists had begun studying this phenomenon in careful detail using objects known as black bodies. A black body is an idealized system that absorbs nearly all radiation that falls upon it, and then re-emits energy purely according to its temperature. In practice, scientists created good approximations of black bodies by constructing hollow cavities with tiny openings. Radiation entering the cavity would bounce around repeatedly until it was absorbed by the interior walls. The small opening then emitted radiation that depended only on the temperature of the cavity itself. Laboratories across Europe began measuring this radiation with impressive precision. Among the most advanced facilities was the Physikalisch-Technische Reichsanstalt in Berlin, a national laboratory devoted to extremely accurate measurement. Scientists there carefully recorded how much radiation was emitted at different wavelengths for objects heated to various temperatures. The results were beautifully consistent. For any given temperature, the radiation intensity rose smoothly to a peak at a particular wavelength, and then gradually declined again at shorter wavelengths. But when physicists tried to calculate this curve using classical physics, something went very wrong. Using the established laws of electromagnetism combined with classical statistical mechanics, theorists predicted that the energy emitted by a black body should increase dramatically as the wavelength became shorter. In fact, the calculations suggested that the energy would rise without limit in the ultraviolet region of the spectrum. According to the equations, heated objects should release enormous amounts of ultraviolet radiation. The predicted curve did not level off. It simply climbed higher and higher, heading toward infinity. This prediction became known as the Ultraviolet Catastrophe. The name sounds dramatic, but the catastrophe occurred inside the mathematics rather than in the laboratory. Experiments clearly showed that real objects did not behave this way. The radiation curve rose to a peak and then declined at shorter wavelengths. The predicted explosion of ultraviolet energy simply did not occur. Something in the theory was fundamentally wrong. At the University of Berlin, a German physicist named Max Planck began studying this problem with great care. Planck was not someone looking to overturn the foundations of physics. Quite the opposite. He had spent much of his career working within the traditional framework of thermodynamics, trying to deepen the understanding of energy and heat. Planck believed strongly in the reliability of physical law. His goal was to reconcile theory with experiment rather than to invent something radically new. Yet the blackbody problem stubbornly resisted conventional explanations. After years of effort, Planck eventually proposed a solution that was both mathematically successful and conceptually surprising. He suggested that energy might not be emitted in a continuous flow, as classical physics assumed. Instead, energy could only be released in discrete packets. These packets became known as quanta. Planck introduced the idea in 1900 while presenting his work to the German Physical Society in Berlin. His proposal stated that the energy emitted by a vibrating system could occur only in specific amounts proportional to its frequency. The relationship can be expressed through a simple equation that later became one of the most famous in physics. Energy equals Planck's constant multiplied by frequency. In spoken form, the equation is simply described as energy equals a small constant number multiplied by the frequency of the radiation being emitted. The constant in that relationship became known as Planck's constant. Its value is extraordinarily small. In everyday units, it corresponds to roughly 6.626 times 10 to the power of minus 34 joule-seconds. This number is so tiny that the effects it describes remain invisible in the ordinary world of human experience, but at the scale of atoms and subatomic particles its influence becomes decisive. Planck did not initially believe that energy was truly emitted in discrete units. He viewed the assumption as a mathematical trick that allowed the radiation curve to match experimental data. In his mind, the quantization of energy was a convenient step in a calculation, rather than a literal description of reality. Nevertheless, the result worked perfectly. The equation derived using these discrete energy units reproduced the measured radiation curve with remarkable accuracy. The ultraviolet catastrophe vanished. The predicted energy distribution now matched the observations recorded in laboratories. Behind Planck's thinking lay an important intellectual influence, the work of the Austrian physicist Ludwig Boltzmann. Boltzmann had developed statistical mechanics, a framework for understanding how the behavior of enormous numbers of microscopic particles produces the familiar laws of thermodynamics. His work suggested that the properties of heat and temperature arise from the statistical motion of countless atoms and molecules. Boltzmann's ideas were controversial during his lifetime, but Planck found them deeply insightful. By applying statistical reasoning to the problem of radiation, Planck arrived at his breakthrough. Even so, the full significance of the result was not immediately recognized. At first, the idea of quantist energy appeared to be a technical solution to a specialized problem. The broader implications were not yet obvious. Yet hidden within that simple equation was a profound suggestion. Nature might not be continuous after all. For centuries, physics had assumed that energy could vary smoothly and without interruption. If a system contained a certain amount of energy, it could in principle contain slightly more or slightly less. The values could change continuously, like water flowing smoothly along a river. Planck's proposal hinted at something different. Energy might come in indivisible steps. Instead of flowing continuously, it might jump between specific allowed values. The analogy often used is that of a staircase. A person standing on a staircase cannot stand halfway between steps. They must occupy one step or another. In a similar way, energy might exist only in certain permitted amounts rather than in every possible value. At the time, the idea felt deeply strange. Planck himself remained cautious about interpreting the concept too literally. But the mathematics was clear, and the experimental agreement was undeniable. Without quite intending it, Max Planck had opened a door into a new understanding of the microscopic world, and once that door was opened, other physicists would soon begin exploring what lay beyond it. The strange idea that energy could exist in discrete packets would soon reach far beyond heated objects and glowing cavities. It would begin to reshape the understanding of light itself. At the beginning of the 20th century, the nature of light seemed thoroughly understood. For decades, the wave theory of light had stood on very solid ground. James Clerk Maxwell's electromagnetic theory had shown that light was an electromagnetic wave traveling through space as oscillating electric and magnetic fields. The equations describing these waves matched experiment beautifully. They predicted radio waves, explained reflection and refraction, and described how light propagates through empty space at a constant speed. By the early 1900s, the wave description of light had become one of the most successful theories in all of physics. Yet, as sometimes happens in science, a small experimental puzzle quietly suggested that the story might not be complete. The puzzle involved what became known as the photoelectric effect. The photoelectric effect occurs when light shines onto a metal surface and causes electrons to be ejected from that surface. These electrons, which normally remain bound inside the metal, suddenly escape when illuminated by light of sufficient energy. This phenomenon had been observed in laboratories during the late 19th century, but its detailed behavior proved difficult to explain using classical wave theory. One of the physicists who studied the effect closely was the German experimentalist Philipp Lenard. Working with carefully prepared metal surfaces and vacuum tubes, Lenard measured how electrons were emitted when different types of light struck the metal. The results revealed several unexpected features. First, electrons were emitted almost instantly when the light struck the surface. There was no noticeable delay, even when the light was extremely weak. Second, the energy of the emitted electrons depended on the frequency of the incoming light rather than its brightness. High-frequency light, such as ultraviolet light, could eject electrons with greater energy, while lower-frequency light produced weaker electrons. Third, increasing the intensity of the light increased the number of electrons emitted, but it did not increase their individual energy. From the perspective of classical wave theory, these results were puzzling. If light were purely a wave, then increasing the brightness of the wave should deliver more energy to the electrons. Under that assumption, brighter light should cause electrons to be emitted with greater energy. Yet experiments showed something different. The energy of the electrons depended on the color or frequency of the light rather than its intensity. In 1905, a young physicist working in Switzerland offered an explanation that would fundamentally change the understanding of light. His name was Albert Einstein. At the time, Einstein was working at the Swiss Patent Office in Bern, reviewing technical applications for electrical devices. Despite the modest setting, he spent much of his spare time thinking about deep questions in physics. In a remarkable year that later became known as his miracle year, Einstein published several groundbreaking papers. One of them addressed the photoelectric effect. Einstein proposed that light does not always behave as a continuous wave. Instead, under certain conditions, it behaves as if it consists of individual packets of energy. These packets were later named photons. Einstein's idea built directly upon Max Planck's earlier proposal that energy could be emitted in discrete units. Planck had introduced this concept while studying radiation from heated objects. Einstein took the idea further by suggesting that the light itself might exist in these discrete units. According to Einstein's explanation, each photon carries a specific amount of energy determined by its frequency. Higher frequency light corresponds to photons carrying more energy, while lower frequency light corresponds to photons carrying less. The relationship between photon energy and frequency can be described by the same equation introduced earlier by Max Planck. Energy equals Planck's constant multiplied by frequency. This simple relationship provided a clear explanation for the behavior of the photoelectric effect. If a photon strikes an electron inside a metal and carries enough energy, it can knock the electron free from the surface. If the photon's energy is too low, the electron remains bound inside the metal. Increasing the brightness of the light increases the number of photons striking the surface, which increases the number of emitted electrons. But the energy carried by each photon remains determined by the frequency of the light. The puzzle suddenly made sense. Light behaved like a stream of tiny energy packets rather than a smooth wave delivering energy continuously. At first, Einstein's proposal was greeted with considerable skepticism. Many physicists were reluctant to abandon the well-established wave description of light. After all, wave behavior had been confirmed by numerous experiments involving interference and diffraction. Even Max Planck himself, whose work inspired Einstein's idea, was initially cautious about accepting the concept of light particles. For more than a decade, the debate continued. Eventually, further experiments provided strong evidence supporting Einstein's explanation. Among the most important were the careful measurements conducted by the American physicist Robert Millikan. Millikan had originally set out to test Einstein's theory in order to disprove it. Yet after performing extremely precise experiments, measuring the energies of electrons emitted from metal surfaces, he reached the unexpected conclusion. The data matched Einstein's predictions perfectly. Despite his initial doubts, Millikan confirmed that the energy of the emitted electrons depended exactly on the frequency of the incoming light, just as Einstein's theory required. The photoelectric effect had revealed something profound. Light could behave as a wave in some situations and as a collection of particles in others. This idea challenged the comfortable certainty that physics had enjoyed during the 19th century. The simple categories that had once seemed so clear, waves on one side and particles on the other, were beginning to blur. In time, the concept of photons became widely accepted. The discovery proved so important that Albert Einstein received the Nobel Prize in Physics in 1921 for his explanation of the photoelectric effect rather than for his later work on relativity. The implications reached far beyond the behavior of light. If electromagnetic radiation could sometimes behave like particles and sometimes like waves, then the distinction between these two fundamental descriptions of nature might not be as rigid as once believed. The boundary between wave and particle was beginning to dissolve, and once physicists accepted that light possessed both kinds of behavior, an intriguing question naturally followed. Perhaps light was not unique. Perhaps the particles making up matter might also possess hidden wave-like properties waiting to be discovered. Once physicists accepted that light could behave both as a wave and as a collection of particles, a curious symmetry began to suggest itself. For centuries, the scientific picture had been comfortably divided into two separate categories. Matter consisted of particles. Light consisted of waves. Each behaved according to its own rules, and the boundary between the two seemed clear. But Albert Einstein's explanation of the photoelectric effect had already disturbed that neat separation. Light, long described as a wave, sometimes behaved as if it were made of individual particles called photons. If waves could behave like particles, one young physicist wondered whether the reverse might also be true. His name was Louis de Broglie. De Broglie was a French physicist working in Paris during the early 1920s. At the time, he was studying the puzzling behavior of atoms and electrons, trying to make sense of the strange new ideas emerging from quantum theory. De Broglie proposed a simple but radical possibility. Perhaps particles of matter also possess wave-like properties. In everyday life, this idea seems almost absurd. A baseball does not spread out like a ripple on water. A grain of sand does not form interference patterns like waves on the surface of a pond. Yet de Broglie suggested that at extremely small scales, the particles making up matter might behave differently from the objects familiar in everyday experience. He proposed that every particle with momentum should also be associated with a wavelength. In other words, matter itself might exhibit wave behavior. This relationship can be expressed with the simple rule linking wavelength to the momentum of the particle. In spoken form, the relationship can be described as wavelength equals Planck's constant divided by momentum. Here, Planck's constant is the same extraordinarily small number introduced by Max Planck while studying radiation from heated objects. Momentum refers to the motion of the particle. combining its mass and velocity. Because Planck's constant is so tiny, the wavelength associated with large objects is unimaginably small. For something like a baseball moving through the air, the wavelength would be far smaller than the size of an atom, making the wave behavior completely undetectable. But for extremely small particles such as electrons, the wavelength becomes comparable to the dimensions of atomic structures. In that realm, the wave nature of matter might become visible. At first, de Broglie's idea was little more than a theoretical proposal, yet the idea was elegant enough that it quickly attracted attention. Among those impressed by the proposal was Albert Einstein, who recognized that the concept might offer deep insight into the strange behavior of atoms. The real test, however, would come from experiment. In the late 1920s, two American physicists working at Bell Telephone Laboratories began studying how electrons scatter when they collide with metal surfaces. Their names were Clinton Davison and Lester Germer. The experiment involved directing a beam of electrons toward a crystalline nickel target. Inside the metal, the atoms of nickel are arranged in a regular repeating pattern known as a crystal lattice. If electrons behaved purely as particles, they would simply bounce off the surface in a somewhat scattered fashion. But if electrons possessed wave properties, something different should happen. Waves encountering a regular structure can produce a phenomenon known as diffraction. Diffraction occurs when waves pass through narrow openings or interact with repeating patterns, causing them to spread and interfere with one another. Light waves produce such patterns when passing through fine slits or crystal structures. If electrons behaved like waves, then scattering from a crystal lattice should produce similar interference patterns. When Davison and Germer performed their measurements, they observed exactly that. Instead of scattering randomly, the electrons formed clear diffraction patterns. The angles at which electrons were most strongly detected matched precisely the wavelengths predicted by de Broglie's equation. Electrons were behaving like waves. Around the same time, an independent confirmation arrived from another experiment conducted in England by the physicist George Paget Thomson at the University of Aberdeen. Thomson directed beams of electrons through extremely thin metal foils and recorded the patterns that formed when the electrons struck photographic plates behind the foil. Rather than simple spots corresponding to particle impacts, the plates revealed circular rings characteristic of wave interference. The patterns matched the predictions for electron wavelengths with remarkable accuracy. An interesting historical detail adds a touch of symmetry to this story. George Paget Thomson was the son of J.J. Thomson, the physicist who had discovered the electron several decades earlier and had interpreted it as a tiny particle. Now the son had demonstrated that this very particle could behave like a wave. The discoveries by Davison, Germer and Thomson provided powerful experimental confirmation of de Broglie's idea. Matter, it seemed, could indeed possess wave-like properties. This realization carried enormous consequences. The traditional categories of wave and particle were no longer separate. Light could behave as a particle, and particles could behave as waves. At the smallest scales of nature, the familiar distinctions that guided classical physics were beginning to dissolve. Electrons inside atoms were not simply tiny spheres orbiting the nucleus like miniature planets. Instead, their behavior appeared more like standing waves distributed through space. Describing such behavior required new ways of thinking. Classical mechanics, with its precise trajectories and predictable paths, could not capture the strange patterns emerging from these experiments. A new mathematical framework would be needed to describe how these wave-like particles move, interact, and evolve over time. physicists were beginning to realize that the microscopic world obeyed rules quite different from those governing everyday objects. Understanding those rules would require an entirely new theory. By the middle of the 1920s, physicists had accumulated a growing collection of experimental clues suggesting that the microscopic world behaved in deeply unfamiliar ways. Electrons behaved like waves when scattered from crystals. Light sometimes behaved like particles. Atoms emitted radiation only in very specific frequencies. The evidence was clear that classical physics could no longer fully describe what was happening at atomic scales. What was missing was a new theoretical framework, capable of making sense of all these discoveries at once. One of the first breakthroughs came from a young German physicist named Werner Heisenberg. In 1925, while working at the University of Göttingen and collaborating with physicist Max Born, Heisenberg began searching for a way to describe atomic behavior without relying on classical pictures of electrons moving in neat circular orbits around atomic nuclei. Previous models of the atom had attempted to imagine electrons as tiny planets orbiting the nucleus like miniature versions of the solar system. Yet experiments showed that electrons behaved far less predictably than such simple pictures suggested. Heisenberg decided to take a different approach. Instead of trying to visualize the motion of electrons directly, he focused only on quantities that could be measured experimentally. These included the frequencies and intensities of light emitted by atoms when electrons changed energy levels. To organize these measurements, Heisenberg used arrays of numbers arranged in rows and columns. Mathematicians call these arrays matrices. The resulting mathematical system became known as matrix mechanics. Matrix mechanics allowed physicists to calculate the possible energy levels of atoms and predict how electrons could transition between them. The method successfully reproduced the spectral lines observed in experiments, meaning the distinct colors of light emitted by different elements. Although the mathematics was unusual and sometimes difficult to visualize, it worked remarkably well. Around the same time, another physicist approached the problem from a different direction. Erwin Schrödinger, an Austrian physicist working in Zurich, was deeply inspired by Louis de Broglie's idea that particles possess wave-like properties. Schrödinger wondered whether electrons inside atoms might be described not as point particles, but as waves spread through space. In 1926, he developed a new equation that described how these matter waves evolve over time. The equation became known as the Schrödinger equation. In words, the equation describes how the wave associated with a particle changes as time passes and as the particle interacts with forces or potentials in its environment. Rather than predicting a single definite path for a particle, the equation describes a wave function. This wave function contains information about the possible positions and behaviors of the particle. The Schrödinger equation quickly proved extremely powerful. It could be used to calculate the allowed energy levels of atoms with remarkable accuracy, explaining the patterns of spectral lines observed in laboratories. The equation can be described verbally as follows. The rate of change of the wave function over time equals a constant multiplied by the energy of the system acting on that wave function. Though the mathematical form is compact, the idea behind it is profound. Instead of describing particles moving along fixed trajectories, the equation describes a spread-out wave representing many possible outcomes. At first glance, Heisenberg's matrix mechanics and Schrödinger's wave mechanics seem like completely different theories. One relied on abstract mathematical arrays, while the other described waves flowing through space. Yet physicists soon discovered that the two approaches produced identical predictions for physical systems. They were simply two different mathematical languages describing the same underlying reality. One of the physicists who played a crucial role in clarifying this connection was Paul Dirac. Dirac, a British physicist working at the University of Cambridge, had an extraordinary ability to translate complex ideas into elegant mathematical form. In the late 1920s, he developed a more general framework that unified matrix mechanics and wave mechanics within a broader structure. Dirac's work introduced powerful mathematical tools that remain central to quantum theory today. His formulation of quantum mechanics helped simplify calculations and reveal deep connections between different parts of the theory. Dirac also predicted the existence of antimatter through an equation describing the behavior of electrons moving at speeds close to the speed of light. This prediction would later be confirmed experimentally with the discovery of the positron. Another important figure in these early developments was Pascal Jordan, a German physicist who worked alongside Max Born and Werner Heisenberg in Göttingen. Jordan contributed to the development of the mathematical rules governing quantum systems, and played a role in the earlier steps toward what would later become quantum field theory. Quantum field theory eventually became the framework used to describe particles as excitations of underlying fields filling space. As these ideas developed, physicists also began debating what the mathematics actually meant about reality. At the center of these discussions was Niels Bohr, the Danish physicist who directed the Institute for Theoretical Physics in Copenhagen. Bohr hosted gatherings of physicists from across Europe, and these meetings became a hub for discussions about the meaning of quantum theory. Out of these discussions emerged what later became known as the Copenhagen Interpretation. According to this interpretation, the wave function described by the Schrodinger equation does not represent a physical wave in space. Instead, it represents the probability of finding a particle in a particular state when a measurement is made. In other words, quantum mechanics does not predict a single definite outcome for an experiment. Instead, it predicts the probabilities of different outcomes. When a measurement occurs, one of those possibilities becomes the observed result. This idea marked a profound shift in the philosophy of physics. Classical mechanics had been built on the assumption that the universe operates in a deterministic way. If the position and velocity of every particle were known precisely, the future could be calculated exactly. Quantum mechanics suggested something very different. At the smallest scales, nature appeared to be governed not by certainty but by probability. A particle might have a range of possible positions rather than a single definite location. Only when measured would one of those possibilities appear as reality. For many physicists, this conclusion was deeply unsettling. Yet the predictions of quantum mechanics matched experimental results with extraordinary precision. The theory worked, even if its implications challenged long-held assumptions about how the universe should behave. And as physicists continued exploring this strange new framework, the role of probability would soon become one of the most intriguing and controversial aspects of the quantum world. As physicists explored the new mathematical framework emerging in the 1920s, one question quickly became unavoidable. What exactly did the wave function described by the Schrodinger equation represent? The equation itself was remarkably successful. It could predict the energy levels of atoms, explain the patterns of spectral lines observed in laboratories, and describe how electrons behave inside molecules. Yet the wave function at the heart of the theory raised a deeper question. Was this wave something physically real, like a ripple moving across the surface of water? Or was it something else entirely? A major step toward answering this question came from the German physicist Max Born. Working in Göttingen during the mid-1920s, Born studied the mathematical properties of the wave function and proposed an interpretation that would fundamentally shape the meaning of quantum mechanics. Born suggested that the wave function should not be understood as a physical wave in space. Instead, it should be interpreted as a mathematical tool describing probability. More specifically, the wave function provides information about the likelihood of finding a particle in a particular place or state when a measurement is performed. If the wave function is large in a certain region of space, the particle is more likely to be detected there. If the wave function is small in another region, the particle is less likely to appear there. This interpretation transformed the meaning of the Schrodinger equation. Instead of predicting the exact position of a particle at a given moment, the equation predicts a distribution of possible outcomes. It describes probabilities rather than certainties. In spoken terms, the idea can be expressed quite simply. The wave function tells us where a particle might be found, and the square of the wave function represents the probability of finding it there. This insight became known as the probabilistic interpretation of quantum mechanics. At first glance, the idea may seem subtle, yet it marked a profound departure from the way physics had traditionally understood the universe. For centuries, the laws of physics had been deterministic. If the position and velocity of a planet were known at one moment, Newton's equations allowed scientists to calculate exactly where the planet would be at any future time. In such a universe, uncertainty arose only because of incomplete information. If every detail were known perfectly, the future could in principle be predicted with absolute precision. Quantum mechanics suggested something very different. Even if the wave function describing a system were known perfectly, the outcome of a measurement could not be predicted with certainty. The theory provides only probabilities. For example, when an electron is described by a wave function surrounding an atomic nucleus, the theory does not assign a precise orbit to that electron. Instead, it predicts a cloud of possible positions where the electron might be found. When a measurement occurs, the electron appears at one of those locations, yet the exact outcome cannot be predicted in advance. Only the likelihood of each possible result can be calculated. This probabilistic nature of quantum theory raised deep philosophical questions. Was randomness truly built into the structure of nature? Or was the uncertainty simply a reflection of hidden variables that scientists had not yet discovered? These questions sparked some of the most famous debates in the history of physics. At the center of these discussions were Albert Einstein and Niels Bohr. Both physicists had played crucial roles in the development of modern physics, yet their views on the interpretation of quantum mechanics differed sharply. Einstein believed strongly in the idea that physical reality should exist independently of observation. In his view, the probabilistic nature of quantum theory suggested that the theory was incomplete. He suspected that deeper hidden variables might eventually restore a deterministic description of nature. Niels Bohr, by contrast, accepted the probabilistic interpretation as a fundamental feature of the quantum world. According to Bohr, the act of measurement plays an essential role in determining the outcome of quantum experiments. The properties of particles are not fully defined until they are observed. These contrasting viewpoints came to life during a series of remarkable meetings known as the Solvay Conferences. The Solvay Conferences were gatherings of the world's leading physicists held in Brussels during the early 20th century. Organized by the Belgian industrialist Ernest Solvay, these conferences brought together figures such as Albert Einstein, Niels Bohr, Max Planck, Marie Curie, Werner Heisenberg, and Erwin Schrödinger. During the 1927 Solvay Conference, discussions about quantum mechanics reached a particularly intense level. Einstein repeatedly presented thought experiments designed to challenge the probabilistic interpretation of quantum theory. Each time, Bohr carefully analysed the scenario and argued that the predictions of quantum mechanics remained consistent. The debates were spirited but respectful, reflecting a shared determination to understand the true nature of reality. Although Einstein remained skeptical of the probabilistic interpretation, experimental evidence increasingly supported the predictions of quantum mechanics. Over time, the idea that probability lies at the heart of atomic behavior became widely accepted. This did not mean that physicists abandoned the search for deeper explanations. Instead, it meant acknowledging that the most successful theory describing the microscopic world predicted probabilities rather than certainties. Electrons in atoms occupy probability clouds rather than precise orbits. Photons interacting with matter produce outcomes that can only be described statistically. Even radioactive decay, a process occurring inside atomic nuclei, follows precise probability laws rather than deterministic schedules. A particular radioactive atom cannot be predicted to decay at an exact moment. Yet large collections of such atoms follow predictable statistical patterns governed by quantum mechanics. In this way, probability became woven into the fundamental description of nature. The idea was unsettling to some physicists, fascinating to others, and ultimately unavoidable. The deeper scientists explored the quantum world, the more they discovered that uncertainty was not merely a practical limitation. It was built into the structure of the theory itself. And this realization soon led to one of the most famous principles in modern physics, a principle that defined the limits of what can be known about the behavior of particles at the smallest scales. As the probabilistic interpretation of quantum mechanics began to take shape during the 1920s, physicists found themselves confronting an even deeper and more surprising limitation on knowledge itself. The theory was not merely saying that predicting outcomes was difficult, it was saying that certain properties of nature could never be known with perfect precision at the same time. This idea became known as the uncertainty principle. The principle was first articulated in 1927 by the German physicist Werner Heisenberg, one of the central figures in the development of quantum mechanics. Heisenberg had already contributed to the creation of matrix mechanics, and he was deeply involved in the growing effort to understand what the mathematics of quantum theory actually meant about physical reality. His insight arose from studying how measurements affect extremely small systems. In everyday life, measurement seems straightforward. A ruler can determine the position of an object, and a speedometer can measure how fast something is moving. These measurements may contain small errors, but in principle the position and speed of an object can both be determined with very high precision. Classical physics assumed that such quantities always exist simultaneously and can, at least in theory, be measured exactly. Quantum mechanics suggested something quite different. Heisenberg realized that when dealing with particles such as electrons, the act of measurement itself becomes part of the physical interaction. Observing a particle requires interacting with it in some way, usually by sending light or other particles toward it, and detecting how they scatter. At atomic scales, these interactions cannot be made arbitrarily gentle. To see an electron clearly, light with a very short wavelength is required. Short wavelength light corresponds to high-energy photons. When such a photon strikes an electron, the interaction inevitably disturbs the electron's motion. In simple terms, the more precisely the position of the electron is measured, the more its momentum is altered by the measurement process. Momentum, in physics, refers to the quantity describing motion. It combines an object's mass and its velocity, providing a measure of how difficult it is to change that motion. Heisenberg recognized that this disturbance was not simply a technical problem caused by imperfect instruments. Instead, it reflected a fundamental feature of how quantum systems behave. This insight led to one of the most famous relationships in physics. The uncertainty principle can be expressed verbally as follows. The uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to Planck's constant divided by 4 times pi. Although the equation itself appears compact, its implications are profound. The principle states that the more precisely the position of a particle is known, the less precisely its momentum can be known. Likewise, the more accurately the momentum is determined, the less certain the position becomes. The two quantities are linked in such a way that perfect knowledge of both is impossible. It is important to understand that this limitation does not arise because of flawed equipment or incomplete technique. Even with a perfectly designed experiment, the uncertainty would remain. The uncertainty principle reflects the fundamental structure of quantum systems. Shortly after Heisenberg proposed the principle, the American physicist Earl Hesse Kennard provided a rigorous mathematical formulation that clarified the exact relationship between position and momentum uncertainties. Kennard's derivation confirmed that the uncertainty principle follows directly from the mathematical framework of quantum mechanics. It is not an optional interpretation or philosophical addition to the theory. It is embedded in the equations themselves. The consequences of this principle extend deeply into the structure of matter. Inside atoms, electrons cannot occupy precise classical orbits like planets moving around a star. If an electron were confined to a sharply defined path around the nucleus, its position would be known very precisely. According to the uncertainty principle, this would require enormous uncertainty in its momentum. Such uncertainty would imply extremely high kinetic energy, which would make the atom unstable. Instead, electrons exist in probability clouds described by quantum wave functions. These clouds represent regions of space where the electron is most likely to be found. The electron does not travel along a fixed trajectory, but instead occupies a distribution of possible positions. This probabilistic structure stabilizes atoms. Electrons spread out in standing wave patterns around the nucleus, forming the familiar shapes of atomic orbitals. These orbitals determine how atoms bond with one another, how molecules form, and how chemistry unfolds throughout the universe. In this way, the uncertainty principle helps explain why matter itself has structure. Without it, atoms would collapse inward under the attraction between electrons and nuclei, and the familiar world of stable matter would not exist. The uncertainty principle also applies to other pairs of physical quantities beyond position and momentum. Energy and time form another pair connected by a similar relationship. In that case, very short time intervals allow temporary fluctuations in energy. These fluctuations play an important role in processes described by quantum field theory, including phenomena such as virtual particles appearing briefly in empty space. Although the mathematics can become intricate, the central idea remains simple. At the smallest scales of nature, perfect precision is impossible. The universe does not allow exact knowledge of every detail simultaneously. Instead, physical reality is described by ranges of possible values governed by probability and uncertainty. For many physicists, this conclusion was initially unsettling. Albert Einstein, who had contributed so much to the early development of quantum theory, remained deeply uncomfortable with the idea that uncertainty might be fundamental. He suspected that deeper underlying variables might one day restore a deterministic description of nature. Niels Bohr and other supporters of the Copenhagen Interpretation argued that the uncertainty principle was not a temporary gap in knowledge, but a genuine feature of how nature behaves. Experiments conducted over the decades that followed consistently supported the predictions of quantum mechanics. Every attempt to bypass the uncertainty principle ultimately confirmed its validity. Today, the principle stands as one of the central foundations of modern physics. It defines the limits of measurement, shapes the structure of atoms, and plays a role in phenomena ranging from chemical bonding to the behavior of particles inside stars. Yet even as physicists accepted the uncertainty principle, a deeper question began to emerge. If measurement inevitably disturbs a quantum system, then what exactly happens during the act of measurement itself? This question would soon become one of the most mysterious aspects of quantum theory. As quantum mechanics matured during the 1920s, physicists gradually became comfortable using its equations to calculate the behavior of atoms, electrons, and radiation. The mathematics worked extraordinarily well. Predictions about atomic spectra, chemical bonding, and scattering experiments repeatedly matched observations with remarkable accuracy. Yet beneath the success of the calculations, a deeper question quietly lingered. What actually happens when a quantum system is measured? The equations of quantum mechanics describe a system using something called a wave function. This wave function evolves smoothly over time according to the Schrodinger equation, spreading out through space and representing many possible outcomes at once. An electron around an atomic nucleus, for example, is described by a wave function that spreads across a region of space. This wave function represents a range of possible positions where the electron might be detected. But when a measurement is made, something peculiar seems to occur. Instead of observing a spread-out wave, the measurement reveals a single, definite outcome. The electron appears at one particular location rather than everywhere at once. The transition from a range of possibilities to a single observed result is known as wave function collapse. Before the measurement, the electron is described by a wave function representing many possible states. After the measurement, only one of those possibilities becomes the observed reality. This raises a natural question. What causes the collapse? The equations describing the wave function itself do not explicitly explain why one particular outcome occurs rather than another. The Schrodinger equation predicts how the wave function evolves, but it does not describe the moment when probabilities appear to become a definite event. This puzzle became known as the measurement problem. One of the earliest attempts to make sense of this situation emerged from discussions among physicists working in Copenhagen, particularly Niels Bohr and Werner Heisenberg. Their interpretation of quantum mechanics eventually became known as the Copenhagen Interpretation. According to the Copenhagen Interpretation, the wave function represents the complete description of a quantum system prior to measurement. It encodes the probabilities of different outcomes, but does not correspond directly to a physical object moving through space. When a measurement occurs, the wave function collapses to a single outcome consistent with the observed result. In this view, the act of measurement plays a central role in determining the properties of quantum systems. Before measurement, a particle may exist in a superposition of several possible states. After measurement, only one state remains. The Copenhagen Interpretation emphasized that the language of classical physics is necessary to describe measurement results, even though the underlying processes follow quantum rules. For many physicists, this interpretation was pragmatic. It allowed the equations of quantum mechanics to be used effectively, without demanding a fully intuitive picture of what was happening beneath the mathematics. Yet not everyone found the explanation satisfying. In 1932, the Hungarian mathematician and physicist John von Neumann analysed the measurement process in detail and introduced a concept known as the measurement chain. Von Neumann pointed out that a measuring device is itself made of atoms, and therefore should also obey the laws of quantum mechanics. If a quantum system interacts with a measuring instrument, the combined system should evolve according to the Schrodinger equation. In principle, the wave function describing the electron could become entangled with the wave function describing the measuring device. If that happens, both would exist in a combined superposition of possibilities. But then the question simply shifts. If the measuring device is also in a superposition, what finally determines the observed outcome? Von Neumann's analysis suggested that the chain of quantum interactions could extend from the microscopic system being measured through the measuring instrument and even to the sensory organs of the observer. Somewhere along that chain, a definite outcome must emerge. But where? The question became even more intriguing when considered by the Hungarian-American physicist Eugene Wigner. Wigner explored the possibility that the observer's consciousness might play a role in resolving the measurement process. In his famous thought experiment, sometimes called Wigner's friend, he imagined an observer performing a quantum measurement inside a sealed laboratory. From the perspective of the observer inside the lab, the measurement produces a definite result. But from the perspective of someone outside the lab who has not yet observed the outcome, the entire system might still be described by a quantum superposition. The scenario highlights the puzzling relationship between observation and physical reality within quantum theory. Although Wigner later moved away from the idea that consciousness collapses the wave function, the thought experiment illustrated just how strange the measurement problem could become. Over the decades that followed, physicists proposed numerous alternative interpretations of quantum mechanics in an attempt to clarify the role of measurement. Some interpretations suggest that the wave function never collapses at all, but instead branches into multiple possible realities. Others propose hidden variables or modifications to the equations of quantum mechanics. Yet despite these efforts, the measurement problem remains one of the most persistent conceptual puzzles in physics. The equations of quantum mechanics continue to produce extraordinarily accurate predictions. Technologies based on quantum principles, including lasers, semiconductors, and modern electronics, function reliably because the theory works so well. But the deeper meaning of measurement itself remains a subject of active discussion. In a sense, quantum mechanics tells us exactly how to calculate the probabilities of different outcomes, while remaining surprisingly quiet about why a particular outcome occurs in a given experiment. This quiet mystery lies at the heart of quantum theory, and the strange implications of measurement become even more vivid when illustrated through one of the most famous thought experiments ever proposed in physics. One of the most unusual ideas to emerge from quantum mechanics is the concept of superposition. According to the equations describing quantum systems, a particle does not always exist in a single clearly defined state. Instead, it can occupy several possible states at the same time, with the wave function describing a combination of these possibilities. In everyday language, this idea can sound deeply strange, yet mathematically it follows naturally from the Schrodinger equation and from the probabilistic interpretation developed by Max Born. If a particle can exist in several possible states before a measurement is made, then the wave function describing that particle may represent a blend of those states simultaneously. For very small systems such as electrons or photons, experiments have repeatedly confirmed this behavior. In certain experimental arrangements, particles behave as though they occupy multiple paths or positions at once until a measurement forces a definite outcome. During the 1930s, the Austrian physicist Erwin Schrödinger became increasingly uneasy with the way this idea was being interpreted. Schrödinger had helped develop wave mechanics and the equation that bears his name, yet he found the philosophical implications of quantum theory troubling. In particular, he felt that the Copenhagen interpretation might be pushing the idea of superposition into situations where it no longer made sense. To illustrate his concern, Schrödinger proposed one of the most famous thought experiments in the history of physics. Imagine a sealed box containing a living cat. Inside the box is a tiny amount of radioactive material, a Geiger counter capable of detecting radiation, a small vial of poison gas, and a mechanism designed to break the vial if radiation is detected. The radioactive material is arranged so that there is an equal chance that one of its atoms will decay within the next hour. If the atom decays, the Geiger counter detects the radiation. The detection triggers the mechanism, the vial breaks, and the poison is released. If the atom does not decay, nothing happens, and the cat remains unharmed. According to the rules of quantum mechanics, the radioactive atom exists in a superposition of two possibilities before it is observed. One possibility corresponds to the atom decaying, while the other corresponds to it remaining stable. If the atom is truly in a superposition of both states, then the entire experimental setup becomes linked to those possibilities. In that case, the cat would also be in a superposition. In simple terms, the cat would be both alive and dead at the same time, until someone opens the box and observes the result. Schrödinger designed this thought experiment not as a literal prediction about cats, but as a critique of the Copenhagen interpretation. He wanted to highlight how strange the implications of superposition could become when extended from microscopic particles to everyday objects. After all, cats in ordinary life are not observed in states of being both alive and dead simultaneously. The thought experiment therefore raised an important question. Where does the boundary lie between the quantum world of superpositions and the familiar classical world of definite outcomes? For several decades, this question remained unresolved. Physicists knew that quantum superpositions occur at microscopic scales, but they rarely appear in the macroscopic world of everyday experience. The reason for this difference began to emerge through research in the 1970s and 1980s. One of the key figures in this effort was the German physicist H. Dieter Zeh. Zeh explored how quantum systems interact with their surrounding environment and how these interactions influence the behavior of superpositions. Later, the Polish-American physicist Wojciech Zurek expanded these ideas into a detailed framework known as quantum decoherence. Decoherence describes how quantum systems lose their coherent superposition states when they interact with the surrounding environment. In practice, no physical system is perfectly isolated. Even the most carefully controlled experiments involve interactions with air molecules, thermal radiation, electromagnetic fields, or other surrounding particles. Each interaction transfers a small amount of information about the system into the environment. When many such interactions occur, the delicate quantum relationships that maintain superposition begin to break down. The wave function describing the system effectively spreads its information into countless environmental degrees of freedom. The result is that the system begins to behave in a more classical manner. Superpositions that would otherwise be visible become extremely difficult to observe because the environment continually disrupts the coherent relationships between quantum states. In the case of Schrödinger's imaginary cat, the animal interacts with trillions of surrounding particles every fraction of a second. Air molecules, photons of light and thermal vibrations constantly exchange information with the cat and the surrounding box. These interactions cause decoherence almost instantly. The result is that the macroscopic world appears to behave in a classical way even though its underlying components still obey the laws of quantum mechanics. Decoherence does not entirely solve the measurement problem, but it provides an important explanation for why superpositions rarely appear in large objects. At extremely small scales, particles can remain sufficiently isolated to display clear quantum interference effects. At larger scales, environmental interactions rapidly suppress those effects. In recent decades, experimental physicists have even demonstrated superposition in surprisingly large systems. Molecules consisting of hundreds of atoms have been placed into quantum interference experiments under carefully controlled conditions. Such experiments confirm that the boundary between quantum and classical behavior is not defined by size alone but by the degree of interaction with the surrounding environment. When isolation is maintained well enough, even relatively large systems can display quantum properties. Schrödinger's thought experiment, therefore, continues to serve as a powerful illustration of the strange implications of quantum theory. It reminds physicists that the mathematical rules describing atoms and particles can, in principle, extend to much larger systems. The reason everyday objects do not behave in obviously quantum ways lies not in a fundamental boundary, but in the overwhelming influence of their environment. Yet superposition is only one part of the quantum story. When multiple particles interact, the theory predicts an even stranger phenomenon in which the properties of distant particles become linked in ways that seem to defy ordinary expectations. This phenomenon is known as quantum entanglement. As physicists continued exploring the implications of quantum theory, they encountered a phenomenon that seemed to challenge even the most basic assumptions about how the universe is organized. This phenomenon is known as quantum entanglement. Entanglement occurs when two or more particles become linked in such a way that their physical properties are described by a single shared quantum state. Once entangled, the particles cannot be treated as independent systems. Instead, their behaviors remain correlated no matter how far apart they travel. To understand why this idea caused such concern among early physicists, it helps to recall the classical expectation about objects in the universe. In classical physics, objects possess properties such as position, momentum, and orientation that exist independently of observation. If two objects interact and then move far apart, their future behaviors can be described separately. Once separated, what happens to one object should not instantly affect the other. Quantum mechanics suggested something much stranger. In certain situations, particles that have interacted can remain connected through a shared wave function, even after they are separated by enormous distances. If a measurement is performed on one particle, the result immediately determines the corresponding property of the other particle. One of the earliest and most famous discussions of this phenomenon appeared in a 1935 paper written by Albert Einstein, Boris Podolsky, and Nathan Rosen. This paper introduced what became known as the Einstein-Podolsky-Rosen paradox. Einstein and his colleagues designed a thought experiment intended to demonstrate what they believed was an incompleteness in quantum mechanics. They imagined a pair of particles created in such a way that their properties were strongly correlated. For example, the total momentum of the pair might be fixed, so that if one particle moves in one direction, the other must move in the opposite direction. Once the particles separate and travel far away from one another, a measurement of one particle's momentum would instantly reveal the momentum of the other. Similarly, a measurement of position on one particle would determine the position of the other, Einstein found this implication deeply troubling. If the act of measuring one particle instantly determines the state of the other, even when they are separated by vast distances, then information would appear to travel faster than light. This seemed to violate the principles of relativity that Einstein himself had helped establish. Because of this unsettling implication, Einstein famously referred to entanglement as spooky action at a distance. Einstein believed that quantum mechanics must therefore be incomplete. He suspected that hidden variables might exist beneath the theory, variables that would restore a local and deterministic description of physical reality. Niels Bohr and other supporters of the Copenhagen Interpretation disagreed. They argued that entangled systems should be understood as a single quantum entity, even when their components are spatially separated. In this view, the strange correlations predicted by quantum mechanics do not involve signals traveling between particles, but instead arise from the shared quantum state describing the system as a whole. For many years, the Einstein-Podolsky-Rosen paradox remained a philosophical debate rather than an experimentally testable question. Physicists could discuss the thought experiment endlessly, but demonstrating entanglement directly in the laboratory required extremely precise control over quantum systems. Advances in experimental techniques during the late 20th century gradually made such tests possible. Among the scientists who played a central role in this work was the Austrian physicist Anton Zeilinger. Working at the University of Vienna, Zeilinger and his research team conducted a series of groundbreaking experiments demonstrating entanglement using pairs of photons. In these experiments, photons were generated in entangled pairs and then sent in opposite directions through optical systems designed to measure their polarization. Polarization describes the orientation of a light wave's oscillation. Quantum mechanics predicts that the polarization measurements of entangled photons will display correlations that cannot be explained by classical theories based on hidden variables. Zeilinger's experiments confirmed these predictions with remarkable precision. The measurements revealed correlations between photons that had traveled significant distances apart, demonstrating that the particles remained entangled even when separated by kilometers. These results provided strong experimental support for the quantum description of entanglement. Beyond confirming a fundamental feature of quantum theory, entanglement has also opened the door to entirely new technologies. One striking example is quantum teleportation. Despite the dramatic name, quantum teleportation does not involve the instantaneous transport of physical objects through space. Instead, it allows the quantum state of one particle to be transferred to another distant particle using entanglement combined with classical communication. In a typical quantum teleportation experiment, two particles are first prepared in an entangled state. A third particle carrying the quantum state to be transmitted is then brought into interaction with one of the entangled particles. Through a carefully designed measurement, information about the quantum state becomes distributed between the particles. Classical information about the measurement outcome is then transmitted to the distant location, where it is used to reconstruct the original quantum state on the second entangled particle. In effect, the quantum state disappears from the original particle and reappears in the distant one. Experimental demonstrations of quantum teleportation have been performed using photons, atoms, and other quantum systems. Some experiments have even transmitted quantum states across satellite links, spanning hundreds of kilometers. These achievements illustrate how a phenomenon once considered purely philosophical has become a practical tool in emerging technologies such as quantum communication and quantum cryptography. Entanglement therefore represents more than just an unusual prediction of quantum mechanics. It reveals that the structure of physical reality may be more deeply interconnected than classical intuition suggests. Particles that once interacted can remain linked in ways that transcend ordinary spatial separation. And as scientists explored these strange correlations further, entanglement eventually provided a way to test some of the deepest assumptions about the nature of reality itself. By the middle of the 20th century, the strange predictions of quantum mechanics had already been confirmed in many experiments. Atoms behaved according to quantum rules, electrons displayed wave-like properties, and photons could exist in entangled states that linked their behavior across distance. Yet one major question still lingered. Was quantum mechanics truly describing the fundamental structure of reality, or was it simply an incomplete theory waiting for deeper hidden mechanisms to be discovered? Albert Einstein had long suspected the latter. He believed that the probabilistic nature of quantum mechanics indicated that something important was missing. In his view, particles might possess hidden properties that determine their behavior in ways the existing theory did not capture. If such hidden variables existed, they might restore a more intuitive picture of nature in which objects possessed definite properties independent of observation. For many years, this debate remained philosophical. Physicists could argue about interpretations, but it seemed impossible to design an experiment capable of settling the question. Then, in the early 1960s, a quiet breakthrough occurred. The Irish physicist John Bell developed a remarkable theoretical result that transformed the debate from philosophy into testable science. Bell was working at the European Organisation for Nuclear Research, commonly known as CERN, when he revisited the questions raised decades earlier by the Einstein-Podolsky-Rosen paradox. Instead of focusing only on the conceptual arguments, Bell asked whether hidden variable theories could produce the same statistical predictions as quantum mechanics. His analysis led to what is now called Bell's theorem. Bell showed that any theory based on local hidden variables must obey certain mathematical relationships known as Bell inequalities. In simple terms, these inequalities place limits on the strength of correlations that can exist between distant particles if those correlations are produced by hidden variables operating locally. Quantum mechanics predicts correlations that sometimes exceed these limits. This means that if experiments were performed measuring the properties of entangled particles, the resulting data could reveal whether nature obeys Bell inequalities or violates them. If the inequalities were obeyed, hidden variable theories might still be possible. If the inequalities were violated, the predictions of quantum mechanics would be confirmed and local hidden variable explanations would fail. For the first time, the strange philosophical questions surrounding entanglement had become experimentally testable. During the 1970s, the American physicist John Clauser helped perform some of the earliest experiments designed to test Bell inequalities. Working with colleagues, including Stuart Friedman, Clauser studied pairs of entangled photons produced by atomic transitions. The researchers measured the polarization of the photons using detectors placed at different orientations. According to Bell's theorem, the statistical correlations between these measurements should obey certain limits if local hidden variables governed the particles. The experimental results did not follow those limits. Instead, the measurements closely matched the predictions of quantum mechanics. Although these early experiments were groundbreaking, they still left room for possible alternative explanations. Some critics pointed out that imperfections in detectors or experimental design might allow hidden variable theories to survive. Further experiments were needed. In the early 1980s, the French physicist Alain Aspect and his team at the University of Paris conducted a series of increasingly sophisticated Bell test experiments. Aspect's group improved the experimental design in several crucial ways. They developed fast-switching techniques that allowed the orientation of the measurement devices to change rapidly, while the entangled photons were already in flight. This approach reduced the possibility that hidden variables could influence both detectors through prior communication. The results once again violated Bell inequalities and agreed with the predictions of quantum mechanics. Over time, experimental techniques continued to improve. Physicists developed better photon sources, more efficient detectors, and increasingly precise timing systems. One of the most influential modern researchers in this area has been Anton Zeilinger, whose work on entangled photons and quantum communication expanded the experimental possibilities even further. Zeilinger and his colleagues performed Bell tests across large distances, including experiments where entangled photons were transmitted between islands and even between ground stations and satellites. These experiments confirmed that quantum correlations persist even when particles are separated by hundreds of kilometers. In recent years, researchers have worked to close what are known as experimental loopholes in Bell tests. Two major loopholes attracted particular attention. The detection loophole arises when not all particles produced in an experiment are detected. If the detected particles represent only a biased subset of the total, the results might appear to violate Bell inequalities even if hidden variables were present. The locality loophole arises if the measurement device is not sufficiently isolated from one another. In that case, signals traveling at the speed of light might influence both measurements. Modern experiments have addressed both of these challenges simultaneously. By combining highly efficient detectors with carefully separated measurement stations and rapid random switching of detector settings, physicists have conducted what are known as loophole-free Bell tests. Several such experiments were reported in the mid-2010s by independent research groups in the Netherlands, the United States, and Austria. The results were strikingly consistent. The measured correlations between entangled particles violated Bell inequalities exactly as predicted by quantum mechanics. These experiments demonstrated that no theory based on local hidden variables can reproduce the full set of quantum predictions. In other words, the strange correlations predicted by quantum mechanics are not merely artifacts of incomplete knowledge. They appear to be genuine features of the physical world. Particles that share an entangled state can display correlations stronger than anything allowed by classical physics. Importantly, these correlations do not allow information to travel faster than light, preserving the principles of relativity. Instead, they reveal that quantum systems can possess relationships that cannot be explained using classical ideas about separate objects with independent properties. The implications are both subtle and profound. The universe appears to be structured in a way that allows distant particles to remain connected through shared quantum states, even when separated across vast distances. Bell's theorem and the experiments that followed transformed a philosophical debate into a clear experimental conclusion. Quantum mechanics does not merely describe our lack of knowledge about hidden variables, it describes a deeper level of physical reality where entanglement and non-classical correlations are fundamental. And as scientists continued exploring these strange quantum connections, it became increasingly clear that quantum behavior is not just a theoretical curiosity, it is woven deeply into the fabric of the physical world. Among the many strange behaviors predicted by quantum mechanics, one phenomenon stands out for its almost magical quality. It describes particles appearing on the other side of barriers that classical physics insists they should never cross. This phenomenon is known as quantum tunneling. In the everyday world, barriers behave in predictable ways. A ball rolling toward a hill will climb partway up the slope and then roll back down if it does not possess enough energy to reach the top. The ball simply cannot appear on the other side of the hill without first passing over it. Classical physics treats this rule as absolute. If an object does not have enough energy to overcome a barrier, it cannot cross that barrier. The laws of motion leave no room for exceptions. Quantum mechanics, however, describes particles differently. Instead of being localized objects with precise positions and trajectories, particles are represented by wave functions that spread through space. These wave functions describe probabilities rather than fixed paths. Because of this wave-like character, the probability associated with a particle does not always stop abruptly at a barrier. Instead, the wave function can extend slightly into regions that classical physics would forbid. If the barrier is thin enough, there remains a small but not zero probability that the particle will appear on the far side. In other words, the particle has a chance of passing through the barrier even though it does not possess the energy required to climb over it. The particle effectively tunnels through the barrier. The possibility of tunneling first emerged in theoretical discussions during the 1920s as physicists began applying quantum mechanics to the behavior of atoms and molecules. One of the early scientists to explore the concept was the German physicist Friedrich Hund. Hund was studying the structure of molecules and noticed that certain quantum systems could transition between configurations that appeared separated by energy barriers. Classical reasoning suggested that such transitions should be extremely unlikely. Yet quantum calculations revealed that particles could occasionally pass through these barriers by tunneling. Shortly afterward, the Russian physicist George Gamow applied the same idea to nuclear physics. Gamow was investigating radioactive decay, particularly a process known as alpha decay. In this process, an unstable atomic nucleus emits an alpha particle consisting of 2 protons and 2 neutrons bound together. Inside the nucleus, the alpha particle is trapped by a powerful nuclear potential that acts like a barrier surrounding the nucleus. According to classical physics, the particle should remain confined indefinitely because it does not possess enough energy to escape. Yet experiments clearly showed that alpha particles are emitted from radioactive nuclei. Gamow realized that quantum tunneling provided the explanation. The wave function of the alpha particle extends slightly beyond the nuclear barrier. Although the probability is small, there is a finite chance that the particle will tunnel through the barrier and escape the nucleus. This tunneling process determines the rate at which radioactive nuclei decay. The theory successfully explained why different isotopes exhibit dramatically different decay lifetimes. A slight change in the energy or width of the barrier can alter the tunneling probability by many orders of magnitude. Quantum tunneling therefore plays a crucial role in nuclear physics and helps explain why radioactive materials behave as they do. The importance of tunneling does not stop at nuclear processes. It also appears in one of the most remarkable scientific instruments ever developed. In the early 1980s, the physicists Gerd Binnig and Heinrich Rohrer at the IBM Research Laboratory in Zurich created a device known as the Scanning Tunneling Microscope. This instrument exploits quantum tunneling to visualize individual atoms on the surfaces of materials. The microscope operates by bringing an extremely sharp metal tip very close to the surface being studied. The distance between the tip and the surface is often only a few atomic diameters. Under these conditions, electrons in the tip can tunnel through the tiny gap and appear in the surface material. The probability of tunneling depends very strongly on the distance between the tip and the surface. Even a change in distance smaller than the size of an atom can dramatically alter the tunneling current. By carefully scanning the tip across the surface and monitoring the tunneling current, the instrument can map the arrangement of atoms with astonishing precision. The scanning tunneling microscope allowed scientists to directly observe atomic structures that had previously been inferred only indirectly. For their invention, Binnig and Rohrer were awarded the Nobel Prize in Physics. Quantum tunneling also plays a vital role in modern electronics. Semiconductor devices such as transistors rely on the behavior of electrons moving through potential barriers inside solid materials. In extremely small electronic components, tunneling effects can influence how currents flow through circuits. As microelectronic technology has progressed toward ever smaller scales, engineers have had to carefully account for quantum tunneling when designing devices. In some cases, tunneling becomes a challenge that must be controlled or minimized. In other cases, it becomes a useful mechanism exploited deliberately within specialized electronic components. The phenomenon also appears in chemistry and biology. During certain chemical reactions, particles must move through energy barriers separating different molecular configurations. Quantum tunneling can allow atoms, especially light ones such as hydrogen, to pass through these barriers rather than climbing over them. This effect can influence reaction rates in complex molecular systems. In some biochemical processes, tunneling may even assist the transfer of electrons or protons within enzymes, helping facilitate reactions that sustain life. Although these processes occur on scales far smaller than everyday experience, their consequences shape the physical and biological world. Quantum tunneling illustrates how particles governed by wave functions can explore regions of space that classical physics would forbid. Instead of following rigid paths determined by energy barriers, particles exist as probability waves capable of leaking through obstacles. This behavior may seem surprising at first, yet it emerges naturally from the mathematical structure of quantum mechanics. The universe at its smallest scales does not behave like a collection of tiny billiard balls obeying simple rules of motion. Instead, it behaves like a complex system of probability waves capable of displaying behaviors that would appear impossible under classical assumptions. And as experimental techniques have continued to improve, physicists have discovered even more surprising demonstrations of quantum behavior. Some of the most intriguing involve experiments where the timing of observations appears to influence how particles behave, raising new questions about the relationship between time, measurement, and reality itself. Among the many puzzles raised by quantum mechanics, some of the most intriguing involve the relationship between observation and the sequence of events in time. One particularly thought-provoking set of ideas was introduced by the American physicist John Archibald Wheeler. Wheeler was a student of Niels Bohr and later became one of the most imaginative thinkers in theoretical physics. His work ranged from nuclear physics to general relativity, and he played an important role in developing the concept of black holes. Wheeler had a talent for designing thought experiments that pushed quantum ideas to their conceptual limits. One of his most famous proposals became known as the delayed choice experiment. The delayed choice experiment grew out of the famous double-slit experiment, which had already demonstrated that particles such as photons and electrons can behave like waves under certain conditions. In the double-slit experiment, particles are directed toward a barrier containing two narrow openings. If no attempt is made to determine which slit a particle passes through, an interference pattern appears on a screen behind the barrier. This interference pattern is characteristic of waves, It suggests that the particle behaves like a wave that passes through both slits simultaneously and interferes with itself. However, if a measurement is introduced that determines which slit the particle travels through, the interference pattern disappears. Instead, the particle behaves like a localized object passing through one slit or the other. The puzzling question raised by this experiment is whether the particle decides to behave as a wave or a particle while traveling through the apparatus. Wheeler wondered whether it might be possible to postpone that decision until after the particle had already passed through the slits. His delayed choice proposal imagined modifying the experimental setup so that the decision about how to measure the particle would be made only after the particle had already entered the apparatus. For example, the experiment could be arranged so that the particle passes through the slits and begins traveling toward a detection region. Only at the last moment would the experimental apparatus determine whether to measure which path the particle took or to allow the interference pattern to emerge. According to classical intuition, the particle must already have chosen whether it behaved as a wave or a particle when it passed through the slits. Yet quantum mechanics suggests that the measurement choice made later can determine how the particle behaves. If the apparatus is arranged to detect which path the particle took, the particle behaves as though it travelled through one slit. If the apparatus is arranged to measure interference instead, the particle behaves as though it passed through both slits simultaneously. Wheeler emphasized that the decision about how to measure the particle could, in principle, be delayed until after the particle had already entered the experimental apparatus. This idea raised a deeply unsettling question. Does the choice of measurement in the present influence how the particle behaved in the past? Although Wheeler did not claim that the future literally changes the past, the delayed choice experiment revealed how quantum systems resist simple descriptions based on classical cause and effect. The behavior observed in the experiment depends not only on the physical system, but also on how the measurement is ultimately performed. For many years, Wheeler's delayed choice scenario remained a conceptual proposal rather than a practical experiment. As technology improved, however, physicists began designing experiments capable of implementing delayed choice measurements with real particles. Several laboratories around the world successfully performed versions of the experiment using photons traveling through interferometers. In these setups, optical devices such as beam splitters and mirrors guide photons along different possible paths. By rapidly switching elements of the apparatus while the photons are already in flight, researchers can determine whether interference occurs or whether which path information is obtained. Experiments conducted in laboratories across Europe, North America, and Asia consistently confirmed the predictions of quantum mechanics. The behavior observed depends on the measurement configuration even when the measurement choice is made after the photon has entered the apparatus. Researchers at institutions including the Australian National University have played an important role in developing increasingly sophisticated versions of these experiments. Teams working there have implemented delayed choice experiments using advanced optical systems and quantum control techniques designed to test the foundations of quantum mechanics with ever greater precision. These experiments have confirmed that quantum systems cannot be described using simple classical narratives in which particles follow predetermined paths independent of observation. Instead, the experimental results suggest that the properties revealed by measurement are not fixed in advance, but are closely connected to the measurement process itself. It is important to emphasize that these experiments do not allow information to travel backward through time or violate the principles of relativity. Rather, they demonstrate that the classical idea of a particle having a definite trajectory prior to measurement does not apply in the quantum world. Quantum systems are described by wave functions representing multiple possibilities. The measurement determines which of those possibilities becomes the observed outcome. The delayed choice experiment simply illustrates how the final measurement arrangement determines which aspect of the system becomes visible. What appears puzzling from a classical perspective becomes entirely consistent within the framework of quantum mechanics. These results highlight the remarkable flexibility of quantum behavior. Particles can display wave-like interference when experiments are arranged to observe it. The same particles can display localized behavior when experiments measure which path they take. The quantum system itself contains the potential for both behaviors. Which aspect appears depends on how the experiment is conducted. This insight has profound implications for how scientists understand the relationship between observation, information, and physical reality. Far from being a passive act, measurement plays an active role in determining what aspects of a quantum system become part of observable reality. While these ideas may seem abstract, they are not limited to philosophical debates about the nature of measurement. In recent decades, the strange properties of quantum systems have begun to power entirely new technologies. Quantum behavior is no longer confined to thought experiments and laboratory puzzles. It has become the foundation of practical devices that may transform communication, computation, and the future of technology itself. For much of the early 20th century, quantum mechanics seemed like a theory describing an invisible world far removed from everyday life. Electrons orbiting atoms, photons interacting with matter, and probability waves evolving through space all appeared to belong to the realm of abstract physics. Yet over time, those abstract ideas quietly became the foundation of the modern technological world. Many of the devices used daily rely on principles that would make little sense without quantum mechanics. One of the most transformative inventions built upon quantum ideas is the transistor. During the 1940s, researchers at Bell Laboratories in the United States were investigating how electrical signals move through solid materials. At the time, electronic devices relied heavily on vacuum tubes, which were large, fragile, and consumed significant power. Scientists were searching for a smaller and more efficient way to control electrical currents. Among the researchers working on this problem were John Bardeen, Walter Brattain, and William Shockley. Their work focused on a class of materials known as semiconductors. Semiconductors are substances whose electrical conductivity lies between that of conductors such as copper and insulators such as glass. Materials like silicon and germanium belong to this category. Understanding how electrons behave inside these materials requires quantum mechanics. Inside a solid crystal, atoms are arranged in a repeating lattice structure. The electrons within these atoms do not remain confined to individual atoms. Instead, they occupy energy levels that extend throughout the entire crystal. Quantum mechanics describes these allowed energy levels using the concept of energy bands. Electrons can move freely through certain bands, allowing electrical current to flow. Other bands are forbidden regions where electrons cannot exist. The structure of these bands determines whether a material behaves as a conductor, an insulator, or a semiconductor. By carefully controlling impurities added to semiconductor crystals, engineers can manipulate how electrons move through the material. These impurities introduce additional energy levels that allow the flow of charge to be controlled with remarkable precision. This principle lies at the heart of the transistor. In 1947, Bardeen and Brattain successfully demonstrated the first working transistor using germanium. Shortly afterward, William Shockley developed the theoretical understanding that led to the junction transistor design. the transistor functions as a tiny electronic switch capable of controlling current flowing through a circuit. Although the physical device is extremely small, its impact has been enormous. Modern computers, smartphones, and countless other electronic systems contain billions of transistors operating together on microscopic silicon chips. Each transistor relies on quantum principles governing electron behavior within semiconductor materials. Without quantum mechanics, the digital world as it exists today would not be possible. Another revolutionary technology rooted in quantum physics is the laser. The word laser is an acronym for light amplification by stimulated emission of radiation. The idea behind lasers originated in the work of Albert Einstein, who in 1917 described the process known as stimulated emission. In stimulated emission, an excited atom can be triggered to release a photon when it encounters another photon of the same energy. The emitted photon travels in the same direction and has the same frequency as the incoming one. This process allows light waves to become synchronized, producing a beam that is highly coherent and extremely focused. Decades later, physicists Charles Townes and Arthur Schawlow developed practical methods for producing this effect in laboratory devices. Their work led to the first operational lasers in the early 1960s. Lasers quickly became essential tools in science, medicine, and industry. In scientific laboratories, lasers allow researchers to manipulate atoms, measure distances with extraordinary precision, and probe the structure of materials at microscopic scales. In medicine, lasers are used in procedures ranging from delicate eye surgery to the removal of damaged tissue. In communications technology, lasers carry vast streams of information through optical fibers that span continents and oceans. When data travels across the internet through fiber optic cables, it often moves in the form of pulses of laser light guided through glass fibers thinner than a human hair. Quantum mechanics, therefore, plays a quiet but essential role in global communication networks. The influence of quantum physics extends into many other areas of technology as well. Magnetic resonance imaging systems used in hospitals rely on the quantum properties of atomic nuclei interacting with magnetic fields. Digital cameras and imaging sensors detect light using semiconductor materials, whose behavior is governed by quantum energy bands. Light-emitting diodes, commonly known as LEDs, produce illumination through quantum transitions of electrons inside semiconductor crystals. Even the atomic clocks that define the international standard of time rely on quantum transitions occurring within carefully controlled atoms. These clocks measure time by monitoring the precise frequency of radiation emitted during transitions between atomic energy levels. The remarkable accuracy of atomic clocks allows global positioning systems to determine location with astonishing precision. Navigation satellites depend on synchronized atomic clocks to calculate distances based on the travel time of radio signals. In this way, quantum physics quietly guides the navigation systems used in aircraft, ships, and smartphones around the world. What once appeared to be an abstract theory about microscopic particles has become deeply embedded in modern life. Many of the devices that power contemporary society depend on the quantum behavior of electrons, photons, and atoms. Most people using these technologies may never think about the physics operating beneath the surface. Yet every time a computer processes information, a laser transmits data, or a semiconductor chip performs a calculation, quantum mechanics is at work. The strange principles discovered by physicists during the early 20th century now form the invisible infrastructure of modern civilization. And as scientists continue to explore the possibilities of quantum phenomena, entirely new technologies are beginning to emerge. Instead of merely relying on quantum effects within materials, researchers are now learning how to manipulate quantum information itself. For many decades, quantum mechanics was used mainly to describe the microscopic behavior of atoms, electrons, and photons. Physicists applied the theory to explain the structure of matter, the emission of light, and the functioning of electronic devices. But during the late 20th century, a new idea began to emerge. What if the strange properties of quantum systems could be used not only to describe nature, but also to perform entirely new kinds of computation? The origins of this idea are often traced to the American physicist Richard Feynman. Feynman was known for his deep physical insight and his ability to explain complex ideas with remarkable clarity. During the early 1980s, he began thinking about a practical challenge faced by physicists attempting to simulate quantum systems on conventional computers. Classical computers represent information using bits that take on one of two values, commonly described as 0 or 1. By combining large numbers of bits, computers can perform calculations and store information in digital form. However, simulating quantum systems using classical computers becomes extremely difficult as the number of particles increases. The reason lies in the enormous number of possible quantum states that must be tracked simultaneously. Each additional particle dramatically increases the number of possibilities that must be represented. Even powerful supercomputers struggle to simulate systems consisting of only a few dozen interacting quantum particles. Feynman realized that a machine built from quantum systems might naturally perform these calculations. Instead of representing information using classical bits, such a machine could use quantum states themselves as the basis for computation. In 1981, during a conference at the Massachusetts Institute of Technology, Feynman proposed the concept of a quantum computer. The key idea was that a computing device operating according to quantum principles could efficiently simulate the behavior of other quantum systems. In other words, quantum physics could be used to understand quantum physics. Feynman's insight did not immediately produce working machines, but it sparked a new field of research. Several years later, the British physicist David Deutsch at the University of Oxford expanded upon these ideas. Deutsch proposed the concept of a universal quantum computer. A universal quantum computer would be capable of performing any computation that could be described within the framework of quantum mechanics. The fundamental unit of information in such a machine is known as a quantum bit, often called a qubit. Unlike classical bits, which must be either 0 or 1, a qubit can exist in a superposition of both states simultaneously. This means that a collection of qubits can represent many possible combinations of information at once. When qubits interact through quantum operations, the system can explore many computational possibilities in parallel. Another important feature of quantum computing arises from entanglement. Entangled qubits can share correlations that allow information to be processed in ways that classical systems cannot easily replicate. These correlations enable certain quantum algorithms to solve particular problems far more efficiently than conventional computers. One of the most famous examples of such an algorithm was discovered in the 1990s by the American mathematician Peter Shor. Shor developed a quantum algorithm capable of factoring large numbers dramatically faster than the best-known classical methods. Factoring large numbers plays an important role in modern cryptography. Many widely used encryption systems rely on the difficulty of breaking large numbers into their prime factors. Classical computers can perform this task, but the time required increases rapidly as the numbers become larger. For sufficiently large numbers, the calculation can take impractically long. Shor's algorithm showed that a sufficiently powerful quantum computer could perform this factoring task far more efficiently. This discovery had immediate implications for the security of digital communication systems. If large-scale quantum computers were built, some forms of widely used encryption could potentially be broken. At the same time, quantum computing also offers opportunities for developing entirely new forms of secure communication. Research into quantum computing has since expanded rapidly across universities, research laboratories, and technology companies. Institutions such as the University of Oxford have played a major role in developing theoretical frameworks and experimental systems for quantum information processing. Researchers there have explored ways to build qubits using trapped ions, superconducting circuits, and other physical platforms. At the Massachusetts Institute of Technology, scientists have contributed extensively to the development of quantum algorithms, quantum error correction techniques, and experimental quantum devices. Similar work is underway at research centers around the world, including laboratories in Europe, North America, and Asia. Despite the progress made so far, building a practical quantum computer remains a formidable challenge. One of the greatest difficulties arises from a phenomenon known as decoherence. Quantum systems are extremely sensitive to interactions with their environment. Even tiny disturbances from surrounding particles, electromagnetic fields, or thermal vibrations can disrupt the delicate superpositions and entanglements required for quantum computation. When such disturbances occur, the quantum information stored in qubits begins to degrade. Maintaining quantum coherence long enough to perform complex calculations requires extraordinary levels of control and isolation. Researchers have developed sophisticated techniques to address this challenge. These include operating quantum devices at extremely low temperatures, using error correction methods that distribute information across multiple qubits, and designing systems that reduce environmental interference. Experimental quantum processors have already demonstrated small-scale calculations involving dozens or even hundreds of qubits. Although these early devices are not yet capable of replacing conventional computers, they represent important steps toward larger and more powerful quantum machines. Many scientists believe that quantum computers will eventually become valuable tools for solving specific types of problems. These may include simulating complex chemical reactions, designing new materials, optimizing certain large-scale calculations, and analyzing systems that are currently beyond the reach of classical computing. Quantum computing therefore represents an attempt to harness the unusual features of the quantum world for practical purposes. The same principles that once puzzled physicists studying atoms and photons may soon become the foundation of entirely new computational technologies. And the exploration of quantum information does not stop with computing. The strange correlations created by entanglement are also opening the door to new ways of transmitting information securely across vast distances. For most of human history, the security of communication has relied on clever mathematics. Messages have been protected by encryption systems designed to make decoding extremely difficult without the correct key. Modern digital communication systems still depend heavily on this approach. Encryption methods used for internet transactions, financial transfers, and confidential communications often rely on mathematical problems that are extremely challenging for classical computers to solve. The security of these systems rests on the assumption that breaking the encryption would require impractical amounts of time and computational power. Quantum physics introduces an entirely different way of protecting information. Instead of relying solely on mathematical difficulty, quantum communication can exploit the fundamental laws of nature to guarantee security. One of the earliest and most influential ideas in this area was developed during the early 1980s by the physicists Charles Bennett and Gilles Brassard. Working together, Bennett and Brassard proposed a method known as quantum key distribution. Quantum key distribution allows two distant parties to generate a shared secret encryption key by transmitting quantum particles, typically photons, between them. The remarkable feature of this method is that any attempt to intercept or measure the particles inevitably alters their quantum state. Because of this property, eavesdropping becomes detectable. The most famous protocol developed by Bennett and Brassard is known as the BB84 protocol. In the BB84 protocol, the eavesdropper can only learn the value of the key bit that is being transmitted for protocol. In the BB84 protocol, photons are prepared in different polarization states. Polarization describes the orientation of the oscillations of a light wave. Each photon can be prepared in one of several possible polarization directions. These directions represent different quantum states used to encode information. The sender transmits a sequence of photons toward the receiver, with each photon prepared using one of two possible measurement bases. The receiver then measures the incoming photons using randomly chosen bases of their own. After the transmission is complete, the sender and receiver publicly compare which bases they used for each photon, but without revealing the measurement results themselves. Only the measurements performed using matching bases are kept as part of the secret key. If no one has interfered with the photons during transmission, the results will be strongly correlated, allowing the two parties to establish identical keys. However, if an eavesdropper attempts to intercept the photons and measure their states, the act of measurement will inevitably disturb the quantum system. This disturbance introduces detectable errors into the transmission. By analyzing the error rate, the communicating parties can determine whether the key has been compromised. If the error rate remains low, they can proceed with secure communication. If the error rate is too high, the key is discarded and the process begins again. The security of quantum key distribution therefore arises directly from the principles of quantum mechanics. It does not rely on the computational limitations of potential attackers. Instead, it relies on the physical impossibility of measuring quantum states without altering them. Over the past several decades, physicists and engineers have developed increasingly sophisticated experiments demonstrating quantum communication in real-world conditions. One particularly ambitious program has been carried out by researchers at the Chinese Academy of Sciences. Their work includes the development of a satellite known as Mixius, named after an ancient Chinese philosopher. Launched in the 2010s, the Mixius satellite was designed to test quantum communication over extremely long distances. Using specialized optical systems, the satellite generates pairs of entangled photons and transmits them to ground stations separated by thousands of kilometers. Experiments conducted with Mixius successfully demonstrated quantum key distribution between distant locations on Earth. These tests showed that quantum communication can function across distances far greater than those achievable through ground-based fiber optic networks alone. The satellite experiments also demonstrated the distribution of entangled photons between widely separated receivers, providing a platform for future quantum communication networks spanning the globe. Other research groups around the world are working towards similar goals. Laboratories in Europe, North America, and Asia are developing fiber optic quantum communication links connecting cities and research facilities. These networks aim to transmit quantum states across increasing distances while preserving the delicate correlations required for secure communication. Several countries have begun exploring the concept of a quantum internet. A quantum internet would use entanglement and quantum information protocols to connect quantum devices across large networks. Such systems could allow quantum computers, sensors, and communication devices to share information in fundamentally new ways. One of the key challenges in building these networks lies in preserving quantum states over long distances. Photons traveling through optical fibers can be absorbed or scattered by the material, gradually weakening the signal. Maintaining entanglement across large distances therefore requires specialized technologies known as quantum repeaters. Quantum repeaters use intermediate nodes that store and regenerate entangled states, allowing the signal to be extended across much larger networks. Although practical quantum networks are still under development, the progress achieved so far suggests that secure communication based on quantum principles may become increasingly common in the future. The underlying physics offers a level of security rooted not in complex algorithms, but in the basic behavior of nature itself. Any attempt to intercept the communication inevitably alters the system and reveals the intrusion. Quantum communication therefore transforms one of the strangest aspects of quantum mechanics into a powerful technological tool. Yet the peculiarities of the quantum world extend even further. As physicists examine the behavior of quantum fields and particles more closely, they discovered that even the concept of empty space must be reconsidered. According to quantum theory, the vacuum itself is not truly empty at all. For a long time, empty space was imagined as exactly that, empty, a quiet stage upon which matter and energy moved, but which itself contained nothing of significance. In classical physics, the vacuum was simply the absence of particles. Remove all matter and radiation from a region of space, and nothing remained. Quantum physics gradually revealed a very different picture. According to modern theory, even the emptiest region of space is filled with activity at the smallest scales. The framework that describes this idea is known as quantum field theory. Quantum field theory emerged during the 1940s as physicists attempted to combine the principles of quantum mechanics with the theory of special relativity developed by Albert Einstein. Several scientists played crucial roles in building this framework, including Julian Schwinger, Richard Feynman, and Shinichiro Tomonaga. Working independently, these physicists developed mathematical techniques capable of describing how particles interact through underlying quantum fields. Their work eventually earned them the Nobel Prize in Physics. In quantum field theory, the fundamental entities of nature are not particles in the traditional sense. Instead, the universe is described as a collection of fields that extend throughout all of space. Each type of particle corresponds to a particular quantum field. Electrons arise as excitations of the electron field. Photons emerge as excitations of the electromagnetic field. Similar fields exist for other particles such as quarks and neutrinos. In this picture, particles are not tiny objects traveling through empty space. They are localized disturbances or ripples within fields that fill the entire universe. This idea leads to a surprising conclusion about the nature of empty space. Even when no particles are present, the underlying fields remain. And because these fields obey the rules of quantum mechanics, they cannot remain perfectly still. Instead, they undergo tiny fluctuations. These fluctuations arise from the uncertainty principle. The principle connecting energy and time implies that energy can briefly appear and disappear within extremely short intervals. As a result, the quantum vacuum is filled with momentary fluctuations in energy. Pairs of particles and antiparticles may briefly emerge from the vacuum and then vanish again before they can be directly observed. Although these fluctuations occur on extremely small scales, their effects can sometimes become measurable. One of the most striking examples is known as the Casimir Effect. The Casimir Effect was predicted in the 1940s by the Dutch physicist Hendrik Casimir. Casimir studied the behavior of electromagnetic fields in the presence of closely spaced metal plates. When two perfectly conducting plates are placed extremely close together in a vacuum, they alter the possible patterns of electromagnetic fluctuations that can exist between them. Certain wavelengths of vacuum fluctuations are allowed outside the plates, but suppressed between them. This imbalance produces a tiny force pushing the plates together. The force arises not from any classical interaction, but from the structure of the quantum vacuum itself. Experiments conducted in later decades confirmed the existence of the Casimir effect. Using sensitive measurement techniques, physicists detected the small attractive force between closely spaced surfaces. The results matched the predictions derived from quantum field theory. What appears to be empty space therefore contains fluctuating energy capable of exerting measurable forces. Another remarkable phenomenon revealing the influence of quantum fields is the Aharonov-Bohm effect. This effect was proposed in the late 1950s by the physicists Yakir Aharonov and David Bohm. Their work examined how charged particles behave in regions where electromagnetic fields appear to be absent. Classically, if a charged particle travels through a region with no electric or magnetic fields, those fields should have no influence on the particle's motion. However, quantum mechanics predict something subtler. In the Aharonov-Bohm effect, electrons travel along two different paths around a region containing a magnetic field that is confined within a shielded area. The electrons never pass directly through the field itself. Nevertheless, the presence of the magnetic field influences the phase of the electron wave functions. When the two electron paths later recombine, the interference pattern shifts depending on the strength of the enclosed magnetic field. This effect demonstrates that electromagnetic potentials can influence quantum particles, even in regions where classical forces are absent. Experiments performed in laboratories confirmed the predictions of Aharonov and Bohm with remarkable precision. The result reveals that quantum particles respond not only to local forces, but also to the broader structure of the field surrounding them. The vacuum, therefore, is not merely a passive backdrop. It is an active environment filled with fluctuating quantum fields, capable of influencing physical processes. These fluctuations may contribute to phenomena ranging from atomic energy shifts to subtle forces measurable in precision experiments. In some theoretical models, vacuum fluctuations may also play roles in particle physics and cosmology. Physicists studying quantum field theory continue to investigate how these fluctuations interact with gravity, matter, and the large-scale structure of the universe. Although the vacuum may appear empty when viewed with ordinary instruments, its underlying quantum structure reveals a restless landscape of constantly shifting fields. Tiny fluctuations occur throughout space, emerging and fading on unimaginably small timescales. This picture challenges the classical idea that nothingness is truly nothing. Instead, even the emptiest regions of the universe contain a dynamic sea of quantum activity. And as physicists began considering the implications of this restless vacuum, a deeper possibility emerged. The strange behavior of quantum fields may not only influence microscopic particles, but could also shape the structure and evolution of the universe itself. The strange principles of quantum mechanics might seem relevant only to the smaller scales of nature. Electrons moving through atoms, photons traveling through optical fibers, or particles interacting inside accelerators all operate within the microscopic world. Yet modern cosmology reveals that quantum physics also played a profound role in shaping the larger structures in the universe. To understand this connection, it helps to consider the conditions that existed shortly after the beginning of cosmic expansion. According to the Big Bang model, the early universe was extremely hot, dense, and rapidly evolving. Matter and radiation were packed together under conditions far more extreme than anything that exists today. During this early period, the entire observable universe was compressed into a region far smaller than it is now. At such enormous densities and temperatures, the laws of quantum physics become inseparable from the large-scale behavior of space itself. One of the most important ideas connecting quantum physics with cosmology is known as cosmic inflation. Cosmic inflation was proposed during the early 1980s by the American physicist Alan Guth. Guth was studying certain puzzles in the standard Big Bang model. One of these puzzles involved the remarkable uniformity of the universe. When astronomers observe the cosmic microwave background radiation, which is the faint afterglow of the early universe, they find that its temperature is nearly identical in every direction. Regions of space separated by vast distances appear to share almost exactly the same properties. This uniformity raises an interesting question. How could distant regions of the universe have coordinated their conditions if there had not been enough time for light or information to travel between them? Another puzzle involved the geometry of the universe. Observations suggested that space appeared extremely close to geometrically flat, meaning that the large-scale curvature of the universe was remarkably small. Without some special explanation, such a precise balance seemed unlikely. Alan Guth proposed that these puzzles might be solved if the universe underwent a brief period of extremely rapid expansion during its earliest moments. In the inflationary model, space itself expanded at an extraordinary rate for a very short period of time. During this brief phase, regions of space that were once extremely close together were stretched to enormous separations. This rapid expansion could explain why distant regions of the universe appear so similar. Before inflation occurred, those regions were close enough to interact and share the same physical conditions. Inflation then stretched them apart, preserving that uniformity across vast distances. The idea of inflation quickly attracted attention from other physicists exploring the earliest moments of the cosmos. One of the scientists who made significant contributions to the development of inflationary theory was the Russian physicist Andrei Linde. Linde developed models known as chaotic inflation and later eternal inflation, which described how inflation might arise naturally from quantum processes in the early universe. In these models, the expansion of space is driven by a field whose energy density temporarily dominates the dynamics of the universe. Quantum fluctuations in that field can produce slightly different conditions in different regions of space. These fluctuations play a crucial role in explaining the origin of cosmic structure. Even though inflation smooths out the universe on large scales, quantum mechanics ensures that tiny fluctuations remain. During the inflationary expansion, these microscopic quantum fluctuations are stretched to astronomical sizes. Regions that once differed by tiny quantum variations become the seeds of future cosmic structure. Over billions of years, gravity amplifies these small variations in density. Matter gradually gathers into clumps, forming stars, galaxies, and enormous clusters of galaxies spread across the cosmos. Observations of the cosmic microwave background radiation have revealed subtle variations in temperature that correspond to these early density fluctuations. Measurements conducted by missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have mapped these fluctuations with remarkable precision. The patterns observed match the predictions made by inflationary cosmology combined with quantum fluctuations in the early universe. In this way, the large-scale structure of the cosmos may ultimately trace its origins to quantum events occurring in the earliest moments after cosmic expansion began. The galaxies scattered across billions of light-years may have grown from fluctuations that once existed on subatomic scales. Quantum physics therefore provides a bridge between the smallest and largest aspects of nature. The same principles that describe particles inside atoms may also influence the evolution of the entire universe. This remarkable connection has become one of the most fascinating themes in modern physics. Cosmologists now combine quantum theory with general relativity to construct models describing the birth and evolution of the universe. Although these models have achieved great success in explaining many observations, important questions remain. General relativity describes gravity as the curvature of space and time, while quantum mechanics governs the behavior of particles and fields. Yet these two powerful theories are not fully unified. At extremely small distances or extremely high energies, such as those present during the earliest moments of cosmic history, a deeper theory combining both frameworks may be required. Physicists therefore continue searching for a more fundamental description of nature. The strange rules discovered in the quantum world may ultimately hold the key to understanding gravity, space, and time themselves. By the early 20th century, physicists had constructed two extraordinarily successful descriptions of nature. Quantum mechanics revealed the rules governing atoms, particles, and the microscopic world. General relativity, developed by Albert Einstein, described gravity as the curvature of space and time produced by mass and energy. Each theory has been tested repeatedly and has demonstrated astonishing accuracy within its domain. Quantum mechanics explains the structure of atoms, the behavior of electrons, and the interactions of particles in high-energy experiments. General relativity successfully predicts the motion of planets, the bending of light around massive objects, and the behavior of black holes and expanding space. Yet despite their success, these two pillars of modern physics do not fit together easily. Quantum mechanics describes nature in terms of probability, wave functions, and discrete interactions. General relativity describes space and time as a smooth geometric fabric whose curvature guides the motion of matter and light. When physicists attempt to apply both theories simultaneously, contradictions arise. This difficulty becomes especially important under extreme conditions where both quantum effects and strong gravitational fields are present. Such conditions occur near the centers of black holes and during the earliest moments of cosmic expansion. To understand these situations, physicists believe that a deeper framework known as quantum gravity must exist. Quantum gravity aims to unify the principles of quantum mechanics with the gravitational description provided by general relativity. Developing such a theory has proven to be one of the most challenging problems in modern science. Several promising approaches have emerged, each attempting to describe gravity in a way compatible with quantum principles. One of the most widely studied approaches is known as string theory. String theory proposes that the fundamental building blocks of nature are not point-like particles, but extremely tiny vibrating strings. These strings are imagined as one-dimensional objects whose different vibration patterns correspond to the various particles observed in nature. Electrons, photons, and other particles would therefore represent different vibrational modes of the same underlying string. This idea emerged during the late 20th century and was developed extensively by many theoretical physicists. Among the most influential contributors to string theory is the American physicist Edward Witten. Witten's work helped unify several earlier versions of string theory into a broader framework known as M-theory. Another important figure in this field is Leonard Susskind, who helped develop key ideas about how strings might describe the fundamental structure of the universe. String theory suggests that space may contain additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. These extra dimensions would be extremely small and tightly curled, making them difficult to detect directly. Although string theory remains a theoretical framework rather than an experimentally confirmed model, it provides a mathematically rich approach to combining quantum physics with gravity. Another major research program pursuing quantum gravity follows a different path. This approach is known as loop quantum gravity. Loop quantum gravity was developed primarily by physicists including Carlo Rovelli and Lee Smolin during the 1980s and 1990s. Instead of introducing strings as fundamental objects, loop quantum gravity attempts to quantize space itself. In this framework, space is not infinitely smooth, but is composed of tiny discrete units connected through networks known as spin networks. These networks represent quantum states of geometry. According to loop quantum gravity, areas and volumes may exist only in discrete amounts rather than varying continuously. The theory suggests that space at the smallest scales may resemble a woven fabric of quantum connections. Time itself may also emerge from the evolution of these networks. Although loop quantum gravity differs from string theory in many details, both approaches share an important idea. The smooth spacetime described by general relativity may not be fundamental. Instead, space and time could emerge from deeper quantum structures operating at extremely small scales. Research into these ideas is carried out at universities and theoretical physics institutes around the world. One important centre for such work is the Perimeter Institute for Theoretical Physics located in Waterloo, Canada. The Perimeter Institute brings together scientists studying quantum gravity, cosmology, and the foundations of quantum mechanics. Researchers there and similar institutions explore how the principles of quantum theory might reshape our understanding of space, time, and gravity. Although a complete theory of quantum gravity has not yet been achieved, progress continues through mathematical models, conceptual insights, and connections between different areas of physics. These investigations suggest that the familiar picture of spacetime may be only an approximation valid at large scales. At extremely small distances, perhaps close to the scale sometimes called the Planck length, the structure of space may become granular or discrete. In such a picture, the geometry of the universe would no longer be continuous, but would instead consist of fundamental quantum units. If this idea proves correct, it would represent a profound shift in how physicists understand the nature of reality. Space and time themselves would become quantum objects rather than smooth backgrounds. The search for quantum gravity therefore pushes physics towards some of the deepest questions about the universe. It asks whether the fabric of reality is ultimately continuous or discrete, and whether the laws governing space and time arise from deeper quantum principles. As these investigations continue, another intriguing idea has begun to attract attention. Some physicists suspect that information itself may play a fundamental role in the structure of physical reality. As physicists pushed further into the foundations of quantum theory, a surprising pattern began to emerge. Many of the deepest questions about reality seem to revolve not only around particles and forces, but around something more abstract: information. The idea that information might play a fundamental role in the structure of the universe was explored by the American physicist John Archibald Wheeler. Wheeler had already contributed to several major developments in 20th century physics, including nuclear physics, general relativity, and the theory of black holes. Later in his career, he proposed a provocative idea summarized in a short phrase, "it from bit." By this phrase, Wheeler suggested that physical reality might ultimately arise from information. In this view, the properties of particles and fields may emerge from answers to basic yes or no questions encoded in the structure of the universe. The term bit refers to the smallest unit of information in computing, representing a choice between two alternatives. Wheeler imagined that the laws of physics might be understood as rules governing how information is processed and organized. Although the phrase may sound philosophical, it reflects a growing connection between quantum theory and information science. Quantum mechanics already describes physical systems in terms of probabilities and states that can carry information. Measurements reveal information about those states, and the act of measurement influences the system itself. As research into quantum computing and quantum communication expanded, physicists began recognizing that information is not merely an abstract description of physical systems. Information is itself a physical quantity that obeys the laws of nature. Another scientist who explored this idea deeply is the physicist Seth Lloyd at the Massachusetts Institute of Technology. Lloyd proposed that the universe itself might behave like a vast quantum computer. In this picture, the evolution of the universe could be interpreted as a continuous process of quantum information processing. Particles interact, fields evolve, and physical systems transform in ways that resemble computational operations. The universe, in a sense, computes its own future state. Lloyd estimated that since the beginning of cosmic expansion, the universe may have performed an enormous number of fundamental logical operations through the interactions of its particles and fields. Although these operations are not organized like the instructions inside a conventional computer, the analogy highlights how deeply information is embedded within physical processes. The connection between information and physics became even more intriguing through developments involving black holes. Black holes are regions of space-time where gravity becomes so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. During the 1970s, the British physicist Stephen Hawking discovered that black holes are not completely black. Using principles from quantum field theory, Hawking showed that black holes emit a faint form of radiation, now known as Hawking radiation. This discovery raised a puzzling question. If black holes slowly lose energy through Hawking radiation and eventually evaporate, what happens to the information contained in the matter that originally fell into them? In classical physics, information about the state of a system should never disappear completely. Yet Hawking's early calculations suggested that black hole evaporation might destroy information entirely. This issue became known as the black hole information paradox. Resolving the paradox has required insights from several areas of theoretical physics. One of the most important developments came from the idea known as the holographic principle. The holographic principle was first proposed by the Dutch physicist Gerard 't Hooft and later expanded by Leonard Susskind. The principle suggests that the information contained within a region of space may actually be encoded on the boundary surrounding that region. In simple terms, the three-dimensional contents of a region might be described by information stored on its two-dimensional surface. The analogy often used is that of a hologram, where a two-dimensional pattern can encode the appearance of a three-dimensional image. If the holographic principle applies to the universe, it would imply that the information describing physical systems might be stored on boundaries in ways that are not immediately obvious. Research into these ideas has advanced through developments in theoretical models connecting gravity and quantum field theory. One particularly influential contribution came from the Argentine physicist Juan Maldacena. Maldacena proposed a relationship between certain gravitational systems and quantum field theories that exist in fewer dimensions. This relationship, often called gauge-gravity duality, provides powerful mathematical tools for studying black holes and quantum gravity. Within this framework, many physicists now believe that information falling into a black hole is not destroyed, but is somehow preserved and encoded in subtle correlations within the radiation emitted as the black hole evolves. Although the full resolution of the information paradox remains an active area of research, these ideas suggest that information plays a central role in the fundamental laws of physics. Quantum mechanics describes how information about physical systems evolves over time. Black hole physics explores how information behaves under extreme gravitational conditions. And theories of quantum gravity increasingly suggest that space-time itself may be connected to patterns of information. Taken together, these developments point toward a remarkable possibility. The deepest level of physical reality may not be composed solely of particles and forces, but also of information encoded within the structure of the universe. As physicists continue exploring these ideas, the picture that emerges becomes increasingly subtle. The quantum world already challenges everyday intuition with superposition, entanglement, and uncertainty. Yet the more deeply scientists investigate these phenomena, the more it appears that reality itself may be built upon layers of information woven into the fabric of space, time, and matter. And with each new discovery, the universe revealed by quantum physics continues to appear stranger than anyone once imagined. The story of quantum physics begins with small puzzles that seemed almost insignificant at the time. A faint glow from heated objects that did not behave quite as expected. Electrons that leapt free from metal surfaces when illuminated by light. Patterns appearing on photographic plates that could not be explained by classical ideas alone. Each puzzle was small, each seemed like a technical problem waiting to be solved. Yet together, these observations opened a doorway into an entirely new description of nature. The journey that followed involved an extraordinary collection of scientists spread across more than a century of research. Max Planck cautiously introduced the idea that energy might come in discrete packets. Albert Einstein proposed that light itself could behave as particles. Louis de Broglie suggested that matter might possess wave properties, a proposal soon confirmed by experiments with electrons. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and Pascual Jordan then helped construct the mathematical framework now known as quantum mechanics. Their work revealed that the behavior of atoms and particles could not be predicted with perfect certainty, only with carefully defined probabilities. Later generations expanded these ideas even further. John Bell demonstrated how entangled particles could test the deepest assumptions about physical reality. Anton Zeilinger and other experimental physicists showed that entanglement is not merely a theoretical curiosity, but a measurable feature of nature. Meanwhile, researchers exploring quantum tunneling, delayed choice experiments, and quantum information discovered that the strange behavior of quantum systems can also produce remarkable technologies. The transistors that power modern computers rely on quantum principles within semiconductor materials. Lasers, medical imaging systems, and modern telecommunications all depend on quantum effects, discovered through decades of careful experimentation. Today, entirely new technologies are emerging from these foundations. Quantum computers aim to harness superposition and entanglement to perform calculations beyond the reach of classical machines. Quantum communication systems promise forms of encryption based on the laws of physics themselves. At the same time, physicists continue exploring some of the deepest questions ever asked. Quantum field theory suggests that even empty space is filled with fluctuating fields. Cosmology connects tiny quantum fluctuations in the early universe with the vast structures of galaxies seen today. And the search for quantum gravity seeks to understand how space-time itself might emerge from deeper principles. After more than a century of investigation, quantum physics has revealed a universe governed not by simple certainty, but by subtle rules involving probability, entanglement, and the flow of information. Yet despite its successes, the theory continues to leave room for mystery. The deeper scientists look into the structure of reality, the more intricate and surprising it appears. At the smallest scales of nature, particles blur into waves, measurements reshape outcomes, and empty space quietly seethes with activity. It is a universe that resists simple intuition, yet rewards careful observation. And perhaps that is part of its quiet beauty. The closer science moves toward the foundations of reality, the clearer it becomes that the universe is not only understandable, but endlessly fascinating.